Okay, so how we're going to work through this question is we're trying to find the net force acting on my 2Q charge. And so what we're going to look at is the forces acting from Q, 4Q, and 3Q. And the first thing I'm going to do is just draw a force diagram for this charge here. Okay, so these two, everything's the same charge, so they're all going to repel. So we have these two. And this is going to be the force due to Q, so I'll label it FQ. The force here from 3Q, F3Q. And what I know is I know that this force is going to be, if this is 1, this is going to be 3 times larger. It's 3 times larger because it's 3 times the charge. The distances between them are the same, so that's going to be 3 times as big of a force as FQ. And so I'm going to try to draw them appropriately so I can get a sense of the direction of what it should be. Okay, the last one would be here. So I need to figure out my distance here, right? I can do Pythagorean's theorem, L squared, so that's 2L squared, and then square root, which gives me the square root of 2L, okay? And they're also going to repel. Now, it's further away, but it is bigger in terms of charge. But what I know is that because our equation for a force, there's a K in there, because it's R squared, this distance has a much bigger impact than the size of the charge itself. So even though it's 4 times bigger than that, it might be kind of equal distant. I don't really know. That's F4Q, okay? So I'm not sure. I know it's going to be smaller than this one, but it might be bigger than that one. I'm not really sure, right? So that gives me a sense of, now if I were to do vector addition, right, add them all head to tail, I could add this here. I could add this, obviously it'd be way up here, and so I would know that the net would be something that looks like that, okay? We'll do that in a different color. My net force would maybe be in that direction. It'd be much longer than what that's drawn, but that can give me a sense of maybe it should be greater, right? It should be greater than 45 degrees in terms of my final angle, okay? So let's now solve for each individual force. FQ, F, 3Q, and F4Q. It's going to be K, Q, 2Q over L squared, which is going to simplify as just 2K Q squared over L squared. Okay? K, Q, 3Q times 2Q over L squared. 6K Q squared over L squared. So we can see that that is 3 times longer, 3 times larger, right? These variables are all the same. These variables are all the same. So this F3Q is 3 times larger than FQ. This one here, K, 4Q, 2Q over radical 2L, that entire thing squared. So that's going to give me 8 here on the top. And this is going to, because that's going to give me 2 there, so that's going to be 4. K Q squared over L squared. All right, so with this one, 2 times 4 is 8. This is going to end up being 2L squared on the bottom, so that can cancel out that, so that's where we get the 4. Okay? So that's how I get my individual values. Then what I'm going to have to do is I'm going to have to figure out how I can get all these together to get my net force on these, okay? So what I'm going to say is this, FQ, is totally just in the X direction, right? F3Q is totally in the Y direction. So F4Q is both in the X and the Y direction, right? So we're going to have to break this apart into its components. So that's the next step that we're going to go through in this problem. Okay, so to break this into its two components, we're going to have both an x component, and there's my y component of that, there's my x component of that, okay? So what I know is because this is a 45, 45, 90 triangle, I know that this angle here is 45 degrees, okay? So what I can do is I can say F4Q and the x is going to be F4Q times, so my x is my same side, so sine, cosine, tangent, right? So katoa, this is the adjacent side, this is my hypotenuse, my 90-degree triangle there. So it's going to be cosine of theta. This is 4k q squared over L squared times the cosine of 45 degrees. So what I can do is I can find this value, which that value is 0.707. And so that just becomes a value, right? It becomes a multiplier. So multiply that by 4, gives me 2.82. And then it's just 2.82 k q squared over L squared. So that's what the x component would be. Now, because it's a 45, 45, 90 triangle, we know that the y component is going to be exactly the same. 8.2 k q squared over L squared. So those are now my x and y components. I can break this down into 2.82 k q squared over L squared. So the last thing then is just to find the sum of all my x components, all my y components, and once I do that, I can build into my net component, right? So if this is my net force, once I have all my x components and all my y components, I can do Pythagorean theorem and I can actually solve for the net force vector. So what that's going to look like is these are my x values. This is an x, and then this is an x. These are my y values. This is a y, and this is also a y. Okay? So putting those together, the sum of the forces in the x direction is going to be Fq plus F4Q in the x, because they're both pointing in that direction, which is going to be 2k q squared over L squared plus 2.82 k q squared over L squared. Those go together, 4.82 k q squared over L squared. So that's my x component. My y component, the sum of the forces in the y, F3q plus F4q in the y, which is 6k q squared over L squared plus 2.82 k q squared over L squared. Add those together, you get 8.82 k q squared over L squared. So those are my two components. Now, to find the total, how would I find the total of this triangle? Pythagorean theorem. Okay, so to solve for my net force, the value or the magnitude is just going to be the net force in the x direction, that value squared. So I'm going to take this and square it. So 4.82 squared, okay? I'm not going to worry about all this because once I square it, this is also going to be squared. So we can add those units together, or we can add these values together once they're squared. And then once we square root, it goes back to this, right? So if we square something and square root it, these variables are going to come back to what they were. So this is going to be plus f net in the y squared. So I'm going to take 4.82 square it plus 8.82 square it, and then square root it. And that gives me 10.1 k q squared over L squared. So that gives me my magnitude. That's how big of a force it is when we have all three of those forces acting together. 10.1, whatever k is, obviously that's a constant, whatever q is, whatever L is. Okay, so it doesn't matter what size of charges these are, right? As long as it's double, triple, quadruple, this is how I can get my actual answer in terms of my magnitude. My direction then is how can I find this angle here? So that's my theta, right? So I'm going to know my x component, I know my y component, so I can use tangent. TOA, right? Tangent equals opposite over adjacent, right? So theta equals tangent of opposite over adjacent. So my y, so that's 8.82 k q squared over L squared divided by 4.82 k q squared over L squared, which when we look at that, these go away. And so we're just taking 8.82 divided by 4.82, okay? And from that, you get a value of roughly 61 degrees. So my answer, my final answer would be 10.1 k q squared over L squared at 61 degrees northeast. Okay? Really useful type of question to be able to work through without any numbers, right? It can be definitely challenging because we have all these variables there. What might be easier is once you get this, right? It might be easier just to ignore this, right? Or just make this as A, right? So you don't really care what those variables are. You could work through this entire problem as FQ is 2A. This is 6A. This is 4A. This is 2.82A. And then you don't really have to worry about all this other stuff. You can just bring it back at the end, because this would be 10.1A. Because A is just all these other variables that are in there. Okay? Hopefully that makes sense. Let me know what questions you have. But that's how you work through question 15.